I don't have that much of an agenda today, but I want to talk about projects, basically. I want to hear what you're doing on projects, any ideas. You know that the project proposal is coming up, and it's due Monday. Actually, I will talk about that a little bit. But I'd like to hear your thoughts on what you're doing on the project, any questions that you may have. Or any questions that you may have on the lectures also. Okay? Yes?
Yeah, could you, since we will do the project and design some method to solve the problem, so could you briefly talk about the metrics we will use to measure the performance and fairness? Because I also have some problem with this data metric.
Okay.
Yeah.
So metrics you will use to measure the goodness of your project, or metrics you will use to measure performance in a multi-core processor? Those are two different topics, right? Unless your project is on the performance of a multi-core processor.
Okay, so the metric to measure the method I designed for my project. I mean, if there are multi-threads running on this system, and I design a method which may more smartly use the memory, or like in my project, the hybrid memories. Compare this method with another original method using the hybrid memories. So we need a metric to measure the performance improvement and the fairness improvement.
Okay, so you're talking about your own particular project. So that's a good start. Okay. Maybe you can tell a little bit more about the project. Basically, you're saying you want to make some optimization. You have a hybrid memory system, let's say some sort of DRAM and phase change memory, and you want to optimize the execution. So what is your idea?
Okay.
That's a good idea. Yeah. Yeah, you can come closer to the microphone too. And hopefully next time we'll have a movable microphone. Yeah. You can briefly describe the idea. And this is exactly what I would like to do actually. Describing the ideas and getting feedback. Yes.
Yes. So right now the problem is that there are multiple threads and we want to run those threads in the system. Basically, we want to make a balance between different threads in terms of the data storage, data mining. Yeah. Okay. So
you want to balance the memory bandwidth between DRAM and phase change memory in a hybrid memory system?
Yes, we actually there are two levels. The first level is that we want to make a balance between the bandwidth of DRAM and PCM for the total memory consumption for all the threads. And then we also the second level is that for each thread we want to partition the data between DRAM and phase change memory.
Okay.
So because we could not put all the data in the DRAM.
Okay. So let me step back a little bit. So you're solving a problem, and the problem is how to more efficiently map data and utilize the memory system when you have a hybrid memory system and multiple different threads. Right. So that's good to. So in your proposal, I would suggest expressing it in this way. You start with a problem. Right.
Yes.
And your goal is to design an efficient mechanism to solve that problem. Right.
Yes.
So your idea is basically what you said. It's like a two-level mechanism. The first is you balance, and this is your initial idea. Yeah. So in your proposal, when you're crafting your proposal, I would say this is our initial idea, and we'd like to balance the memory bandwidth between the two memories, DRAM and phase change memory. And to do this, we have some algorithm. Yeah. And I don't know what your algorithm is, but you can go into that in your proposal. And once the memory bandwidth is balanced across the entire threads, then the second question is how do you actually map the data of each thread to different memories, DRAM versus phase change memory?
Yeah.
Right?
Yes.
Okay. If I understand you correctly.
Yes.
Okay.
So right now I encounter some problems in terms of metrics.
Okay.
I found that there are multiple metrics to measure the system performance.
Okay.
For example, there is like a total throughput.
Okay.
Sigma IPCI.
Okay.
Yeah. And another is like weighted speed up.
Okay.
I think that for my specific problem, I need to compare my method and the previous method.
That's it.
So for the weighted speed up, I have some doubts.
Okay.
It's like, is it because weighted speed up is the
Okay, so I guess I can take it from here. I understand your question. So then the key question is what metric do you use to compare your system, your ideas, versus the baseline, right? I think this goes into the general issue of what kind of metrics do you use to measure the performance of a multi-core processor, especially in simulation, right? Because in simulation, we cannot execute the entire program easily. So you would like to have metrics that are measurable within that time frame. The second is if you have a multi-programmed environment, even if you can execute the entire program, what's a good metric to summarize the entire system's performance, right? And that's what I can briefly touch upon. And this is actually a research topic also. If you have good ideas on how to better measure performance of a multi-core system in a multi-programmed environment, then you could make potential contributions in that too. Okay, so I guess there's several things. Well, it looks like this is old stuff. And this is good for everyone to think about also. Oh, I need 4 fingers. There you go. Okay. That looks good. So what kind of the cores that are executing these different threads, and this is your memory system in this case, and you have potentially a DRAM and phase change memory hanging off your memory system, right? This is the kind of system that you're envisioning, I think. Then how do you measure performance? I think there are several issues. One is the threads that are executing on the cores can be part of a multi-threaded application, right? So they could be cooperating with each other to solve a single problem. In that case, there's no better metric than just execution time, right? You just execute the entire application. And you would like to, if your goal is to maximize performance, then you would like to design a mechanism that minimizes the execution time, right? Does that make sense? Does everybody agree with that? If your goal is just performance. If it's a multi-threaded application where threads are cooperating with each other. And if you have a single multi-threaded application.
Single one, that's right.
Yes, just one application, yes. In that case, there's no better metric than just execution time for performance. Okay. Now the problem becomes more difficult if you have multi-programmed applications, multi-programmed workloads, I'll say. Basically, a combination of, let's start with a simple case. Well, I guess let's start with the even simpler case. You have a single-threaded application, right? Then you're not utilizing all the cores. You have one application running here. Again, execution time is what you would like to minimize, right? In that case. And you can have a single multi-threaded application, which we've just discussed. Now you can have a multi-program workload. And multi-program workload can be formed as multiple single-threaded applications. In which case, you'll have application 1, application 2, application 3, application 4 running on those different cores. Then the question is, how do you actually measure the performance of the system, right? And I'll give you some metrics. And actually, let me bring up another paper also to aid this. You've done some readings, right? Which one should I bring up? There you go. Oh, this is the top picks version. Do we have the ISCA version of this one? You see, the entire world is based on search, right? That's the best way to find anything these days. It's amazing how technology has influenced the way we think and we find information. It used to be that we were able to categorize information in many different ways, but now it's very difficult to categorize information. It's really all about search. So building computer systems that can do this much more efficiently is definitely a good topic. Let me open it up in some other browser that I like better. Because what I seem to be able to do in this browser is this. Okay. So this is one paper that discusses a similar problem, right? Although this is very tightly put up over here. Actually, let me pull up another paper also. I guess I'll have to do this over and over. So these two papers I would recommend, and you will read them later on. They discuss a similar issue, except the problem is different in this case. The problem is what you read earlier about you have unfairness in the memory scheduling logic. And how do you design a memory scheduler that can improve system performance and fairness at the same time? I guess this is the same thing. But you can look at metrics for fairness and throughput here. Let's look at the metrics for performance. So each of these applications, there you go, better. Each of these applications that are executing over here can have some performance, right? One is what you suggested. Each of them can have an IPC. And IPCI is the IPC of the application that's executing on core I. One metric could be the sum of IPCs, right? That's kind of like total instruction throughput that you have. Is this a good metric to measure the total system performance? Some people are doing this, shaking their heads. What do you think? Why is it not a good metric? Or if you think it's a good metric, why is it a good metric? Yes?
It could be a reasonable metric if all your applications are the same. Like if all your threads are just part of, they're homogeneous.
That's right, that could be actually, yeah.
Can you repeat what you said?
So you suggested that if all of your threads are the same, this could be a reasonable metric.
Thank you.
Yeah. So if your goal is to somehow maximize the number of instructions that are executed, this could be a reasonable metric also, right? So even if all your threads are the same, it may not be that good. So I'll challenge that because this doesn't take into account how much progress each thread is making, right? So it may be that even if all your threads are the same, the hardware is, for example, prioritizing one thread a lot and maximizing the IPC that way, right?
Yeah, but some kind of thing is related with fairness.
But it's also related to performance, right? Here, things get a little bit different because you're looking at the multi-program performance. Right? You have different threads. Like, how do you maximize the performance? Ideally, you would like to take all of those threads and execute them and look at the time it takes to execute all of them in system A, and then take the same set of threads and execute them and look at the time it takes to execute all of them in system B, right? And then do that comparison. Well, we cannot do that in simulation because it takes so long to execute all of those different applications, right? So we'll need to find ways of approximating that performance. And this is one way of trying to do that. But this is not a good metric because it's really looking at instruction throughput, right? Instruction throughput may not be related to the entire progress of all of the threads. Right? So people have developed other metrics that take into account a little bit of fairness, as you said, or more progress of other threads relative to when they run alone on the system. and weighted speed up is one metric. And I'll give you references. So this is actually a deep topic. And there's no consensus in the field on how to measure multi-program performance in simulation. So if you have ideas on how to improve this, I'd encourage you to think about it. So weighted speed up is basically, actually let me go over here. It's this one, right? IPC shared divided by IPC alone. Actually, you could think of it as execution time, right? Actually, the hope is that this is equivalent to execution time, right? Yeah. Similarly, with the weighted speed up, it's really the sum of the IPC I shared divided by IPC I alone in a baseline system, in the target or baseline system, depending on where you're measuring. And the idea over here is, in a baseline system, this particular application has some performance, execution time. Oh, yeah, thank you. You can shout. Don't. You guys can tell me also. I don't want to be talking to myself. Okay, I don't know if this is visible. Yeah, so focus on this part. Basically, it's the sum of the speed up. And the speed up is measured compared to this baseline system. This is the performance of the application when it's executing alone on a baseline system. And this is the performance of the application when it's executing together with other applications on the target system or the baseline system. And weighted speed up of, this is assumed to be overall system performance, right? Of system X. And let's call this IPC shared on system X. And you still have a baseline, common baseline system, right? That's the idea. Basically, how much did you speed up an individual program on this system compared to a common baseline system? You sum up those speed ups, and that's your overall system performance. You calculate this for system X, that's your baseline, let's say, and then you calculate it for system Y and compare them.
So, for example, right now we want to calculate it for weighted speed up for system Y. Then the denominator will be the IPC. The denominator will be the when we run multiple threads on this system Y. What each thread IPCI is. This is the denominator. The denominator will be when we ran a single thread on the original system.
Exactly, on the original. So this has to be constant because this is a comparison point. So you can vary the system. You can look at the weighted the overall system performance of system X, Y, Z, T. This should not change. If this changes, there's no common comparison point, right? Because you're trying to figure out, compared to a baseline, common baseline, how much is this particular application speeding up or slowing down? And you're summing up those competitive ratios, if you will, comparative slowdowns or speed ups across all the applications running on that system. Does that make sense?
Yes.
Yes. So it is a reasonable metric to measure performance because it's really trying to tell you how much are you speeding up or slowing down a particular application. Okay? Now you could always argue that this may not be the best metric, right? How does it correlate with execution time, for example? I'll let you think about that. I'll give you actually a couple of papers related to this. It's always good to question the metrics. But this is a commonly accepted metric that's used today in simulation. Because people don't know how to better evaluate the performance, really. There's another metric which we'll talk about, harmonic speed up, which is basically harmonic mean of the speed ups. This is the weighted mean of the speed ups, right? Arithmetic mean. Does that make sense? Does this metric make sense? You'll have to think about it a little bit. Does that answer your question?
Yes.
I think I anticipate what your confusion was. The confusion was, does this vary depending on the system, right?
Yes.
If it varies, if you take this as system X, then it doesn't work, right? If it varies with the system you're measuring, then you're comparing apples and oranges totally. But if this baseline performance of an application is constant on some particular system, it doesn't have to be, it can be any system actually. That makes sense, of course. Then this could give you relative comparison points. Yes?
IPC here, do we refer normally to instructions visible only at the ISA level, or instruction issue? Because I can see a problem, for example, run a execution might issue a lot of extra instructions during a high IPC count.
Yes.
However, those instructions will be fake and not necessarily in progress to the system.
That's it. So that's a good question. Basically, the question is, how do you compute this IPC? Is that the instructions that are retired or instructions that are executed? So this should be retired instructions, committed instructions. Otherwise, you can actually get weird results, right? Run execution could be increasing executed instruction IPC, but it may not be increasing performance. So whenever you compute performance, it should be retired instructions. Or even out-of-order engines you execute on the wrong path, right? You don't want to include them as part of your IPC. Ideally, you would like T, right? Time shared. That includes not only IPC, but also number of instructions times the cycle time, right? But if you're not changing, if you're assuming that the number of instructions is constant and the cycle time is constant across all the systems, then you can use IPC. Yes?
In that case, will execution time be the same as IPC?
In that case, your execution time would correlate with IPC, right? Your performance correlates with IPC. It won't be the same, but...
As in, you can directly derive them from the equation.
That's right, yes, exactly. Yeah, this metric will be the same. Okay? Yeah. So let me give you a couple of papers. So the other metric that's used, in addition to weighted speed up, now I can move here, not to the wrong side, is harmonic mean speed up, which is this one. I don't know if you can see that. That's basically harmonic mean of the speedups instead of weighted mean. Number of threads or number of cores divided by sum of 1 divided by IPC shared divided by IPC alone. And I would suggest using these two metrics if you're doing multi-program performance evaluation. I guess let me give you some papers that talk about these issues. I guess I'll have to go here or here. There are actually some recent papers that talk about this. Finding keywords is the most important part in search. After that, yeah. This is one paper, system level performance metrics for multi-program workloads. So in this paper, what the authors argue is that IPC, sum of IPCs is not a good metric for evaluating multi-program workload performance because it has no correspondence to any execution time. They also argue that weighted speed up is a good metric because so they actually start with some system level performance metrics like turnaround time, job turnaround time. That's what you care about, right? If you have a multi-programmed batch simulation, for example, you care about what is your turnaround time. You also care about how many jobs per second you finish. That's the throughput metric. And turnaround time is another metric. So they show that the weighted speed up metric that we just discussed actually corresponds to system throughput metric, jobs per second, under some assumptions. And the harmonic mean speed up actually corresponds to the inverse of the normalized turnaround time, job turnaround time at the system level. So this is a good paper to read. You can question some of the assumptions and maybe come up with different ways of evaluating system performance, but this is something I would definitely recommend, especially if you're going to evaluate multi-program system performance.
So I ask a quick question.
Yeah.
In some paper, I found normalize the weighted speed up. So it's like speed up divided by n. N is the number of the.
Yes, that's right. That's the normalized way to speed up. You speed up divided by n. But that n factor actually goes away, right?
Yes.
Hopefully you're not changing. So you cannot compare different weighted speed ups across different n's. With a 4-core processor versus an 8-core processor, that comparison of weighted speed up that makes no sense. So you want to keep n constant.
Yeah, but if like there are multiple threads, but the thread execution time, the finishing time is different. Then n is because at each time step maybe there are different ends.
I didn't understand that.
So it's like there are multiple threads run on this system.
Okay.
And maybe the first thread can be complete in like a millicycle or something.
Okay.
And the second thread like complete I just assume like 1 billion cycle is like closing. Then how many threads?
Oh, okay. So now you're getting into real issues and how to do measurement.
Yeah.
That's a tough one. So if a thread actually completes early, how do you take that into account in the system? So if you're actually simulating all of the threads until they end, this is not a problem. You basically add up the execution times. Or you basically look at the beginning of when the multi-program starts and end of when the multi-program execution ends, right? The problem is we cannot do that in simulation. The problem is in simulation, we just have a small sample of execution from each application. And what happens usually is, I should switch now. What happens usually is you're running some number of instructions, right? You have a trace, let's say, 1 billion instructions of application A and 1 billion instructions of application B, and you want to measure performance, right? In the baseline system, what might happen is application A's 1 billion instructions make this much time, and application B's 1 billion instructions may take this much time, right? Assuming time is the x-axis. Now, how do you actually compute performance in this case? How do you compute weighted speed up in this case? This question has puzzled many people. I think it's still puzzling. There's no perfect way. And so this is, let's say, system X. And now you have system Y. Again, application A and application B. And you execute them. The execution may look like this, right? Now you cannot conclude that this system is better than, the system Y is better than system X, because these are just some set of instructions, right? You don't know how, because you're running just portions of the workload, right? Or even you could have different scenarios, right? System Z, application A, application B. A can take shorter, much shorter, and B can take a little bit longer. Now, which system is better? That's a tough question. So in simulation, what we usually do, in real life, this application wouldn't have ended for a long time. One of the assumptions that we make in a lot of the studies that you've been reading is applications will just continue executing. So this application doesn't end after 1 billion instructions, but it keeps exerting pressure into the system. So you don't stop the application. You keep executing it. Now, how do you do that? Well, you take a trace that's much longer than 1 billion instructions, for example. You take a trace that's 100 billion instructions, and you keep executing that. That's one way of overcoming this problem. Well, what problem did we overcome? One of the problems is if this application ends, then you're really not executing the multi-programmed work anymore, right? So we usually keep executing this application. Another way of overcoming this problem, this is more synthetic, is repeating these 1 billion instructions over and over once it ends. Right? Now, this is not a great way, again, but that's what's also accepted in simulation. Because it's a tough problem, right? And if you actually think about it in a little bit broader way, how do you compare these two things? Like, what do you compare? Do you compare equal amount of work, or do you compare equal amount of time across system X and system Y? Ideally, you would like to compare equal amount of work, right? The problem is you cannot execute the entire application again, all of the applications in the multi-program workload. So it's tough to have an equal basis of comparison or equal amount of work. Because if you say I'm going to execute, well, actually, we're trying to get close to equal amount of work, right? Basically, we'll try to measure the performance when I execute 1 billion instructions in each application. That could be one way of trying to equalize the work. If you do that, when this application ends, it stops exerting pressure, so you'll need to continue to exert pressure somehow. Right? Does that make sense? Does this kind of answer your question?
Yes.
Yeah. But then, is it equal amount of work as it keeps continuing, right? So then, let's assume that we've done this. How do you compute weighted speed up? Basically, you look at the execution time of this 1 billion instructions. You basically compute sum of IPC shared divided by IPC alone on this 1 billion portion. And the rest you keep executing, but you do not compute statistics on this. And for this application, you compute IPC shared divided by IPC alone for this 1 billion chunk. Does that make sense? You could argue that it may not make sense, and I would actually agree with you. But this is the best we can do at this point, unfortunately. If you come up with a better methodology, I'm really interested in hearing that. And if this is totally over your head, then I'd encourage you to read some of the papers.
Just measure the like the performance during like two applications are running at the same time. Just like a small, like a shorter one. Just measure at that time.
Oh, measure right here.
Yeah.
So that's another methodology actually. That's a better methodology. Now we're getting at something better, perhaps. So you're suggesting this, right? When one application ends, look at what happens to this application and figure out the number of instructions that is executed, and somehow measure the weighted speed up that way. Right? Now, simulation becomes more complex, right? You need to figure out how many instructions were executed in this particular application, and figure out IPC shared. Well, you have IPC shared in this case, but you need to go back and run IPC alone with this number of instructions. But then you have some other problem now, because what do you do over here? Let's say system X, this application finished 1 billion instructions over here. In system Y, it's finished 1 billion instructions here. Let's say this number of instructions was, I don't know, I1. In this case, you have I2.
So you don't have the same standard, huh?
You don't have the same standard. That's the problem. Yes. At least, if you fix the number of instructions, you have the same standard. 1 billion, 1 billion, everywhere. If you do what you suggest, then you don't have the same standard, and you get weird results. Yeah. Yeah, if you cannot fix the amount of work perfectly, at least have the same standard of comparison. That's the takeaway in how we compute weighted speed up, or harmonic speed up using this methodology. And again, remember, why can't we fix the amount of work? Because we cannot execute the entire application in that simulation level. Ideally, if you execute the entire application, everything is good, right? You just look at when it starts and when it ends, and it's done. And when I say entire application, it's the entire multi-program workload. And this becomes an even harder problem if you have 1,000 cores, right? How do you actually execute 1,000 applications? Okay. Any questions on this? Okay. Yeah, I was giving you some more papers. So I'd encourage you to read this paper. This is a paper I like, and it actually takes a good approach. There's another paper that I would also recommend, if I can get to it. It's a more recent paper. It's a short paper. There you go. This is actually on more fairness metrics, which is actually even a harder problem, right? Because performance, at least we know it is execution time. Fairness, what is fairness? Fairness is different. It's almost in the eye of the beholder, right? But this is a good paper that discusses some of the metrics. And this is in 2011, so you can see that this is actually an ongoing research topic. Okay. I'd encourage you to read that one also. So one of the fairness metrics that we have used in the past is, actually let me go back to this stall time fair memory scheduling paper. Well, this is memory, so let's take a look at this one. This is the I guess I'll ignore that for now. If you figure out the slowdown of a thread, slowdown I of a thread as basically this is the memory slowdown in this case, but it's really the time you take to execute the thread shared divided by time. I guess I'll do this. When the thread is executing alone, again on the baseline system, I guess we can say slowdown on system X. Unfairness of the system, one unfairness metric would be the maximum slowdown across all threads in the system divided by minimum slowdown across all threads in the system. Right? And if your perfect unfairness is 1, where the maximum slowdown is equal to minimum slowdown. Basically, a system is not unfair if unfairness is 1. And as unfairness increases, the system becomes more unfair, right?
And the TI alone is also on the baseline system, but TI shared is on either baseline or.
Exactly, the same thing. TI alone is on a common baseline here. Okay? Yeah. So you have to have that common baseline, otherwise things will be moving. Yeah. So this is one definition of unfairness, basically. Maximum slowdown you have for any thread in the system divided by minimum slowdown you have for any thread in the system. The goal is so to build a fair system, the goal is to equalize. The goal is to make unfairness 1, which means that equalizes slowdowns that you see for any thread. Now, is this a good fairness metric? No? Maybe? Maybe, right? Yes?
Well, you could have a max that's really far out in the spectrum and a mid that's really far out in the spectrum.
Uh-huh.
And that will skew your numbers even if 99% of your applications were mostly fair.
That's right.
There could be just one outsider that could skew this metric.
Exactly, yes. That's right. So this is very strict in one sense. You could have only one thread that has been slowed down a lot, that has a high maximum slowdown, and that could be increasing your unfairness.
But that's your definition of one.
Exactly, yeah. So that's the problem with unfairness metrics. It's hard to, you come up with a fairness metric and define a metric based on that, and it's in the system is evaluated based on the metric you define, right? So this metric is biased towards equalizing everything as much as possible. So another metric, another unfairness metric that we have more recently used is the maximum slowdown metric. This is basically, you can define unfairness as just the maximum slowdown. And the goal in building a fair system is to minimize the maximum slowdown in the system. Right? Basically, this is trying to bound the worst case slowdown of any application in the system. This is less strict in that sense, right? You're trying to minimize the maximum slowdown. But in a sense, you could argue that it doesn't care about this form of fairness as much.
How do you call that fairness?
How do you call this a fairness metric? Because it's really trying to, so if you have a system, let's say system X, and you have let's say 4 threads, slowdowns are 1, 1, 2, 4, and system Y, your slowdowns are, maybe I'll come up with a 1, 1, 2, 3. The maximum slowdown here is 3, and the maximum slowdown over here is 4, right?
But there's no relation between this and the slowdown to other threads and unfairness.
That's right.
By definition, there's this relation.
So that's your definition of fairness now.
No.
Maybe my definition of fairness is what is the worst case slowdown that any thread experiences in the system, right? In that, if you take that point of view of fairness, then maximum slowdown is a good metric. Basically, I'd like to minimize the worst case slowdown that any thread experiences.
Okay, so then you could implement something that reduces the slowdown everywhere, and it would be reflected in this metric. But that
Same here.
No, it won't. I'm saying you're improving all the threads.
Uh-huh.
And your second metric would reflect that, but the first one wouldn't.
Well, give me an example. You're reducing the slowdown of all threads. Or-
Yeah, exactly.
Okay.
You do something that helps all threads,
Okay.
right? So your unfairness metric won't change if you define
In
it
this
that
case,
way,
that's right. Yes.
but it would in this case.
It would in this case. That's right.
how
So
do
let's say
you talk
basically.
about fairness?
Yeah, it's kind of so exactly. Yeah. So the concepts are a little bit mixed here, but the hope is that the metric is good because it's helping you also to improve performance, right?
It's a performance metric. It's not a fairness metric.
It's a mixture. It's not a perfect performance metric because it's not taking into account the entire system, right? So the goal was actually to have a balance between performance and fairness in this case.
That's right.
Because what is your goal in the end? Your goal is to minimize the slowdowns as much as possible. And hopefully, the hope is that will improve performance. And the hope is that will also improve fairness. Now, I'm being very wishy-washy here. It's very hard to be mathematical about this also. That paper, the paper that I just recommended to you, actually goes through, not this one, a lot of metrics, and they also settle down on this maximum slowdown, interestingly. So I'll encourage you to read that paper. That has an argument also, which can be challenged. All of these fairness metrics arguments can be challenged. But what they argue is that gives you a quality of service bound. Basically, maximum slowdown is kind of a quality of service metric. It improves the quality of the service that any thread is getting in the system. Yes?
Well, technically there's a hidden baseline, which is a maximum slowdown of 1.
Uh-huh.
I don't think it's possible that if you add a thread, you can expect an increase in performance.
Mm-hmm.
If they're not in the same cache, of course. So I think maximum slowdown is really implying if we can get a slowdown of 1, then that's ideal because no thread is affecting any other thread.
Mm-hmm.
Otherwise, if you can reduce number, it's better.
Mm-hmm. That's right, yeah. But then you could argue that that's not a fairness metric, which Nandita is arguing.
That's more
Not-
starvation than
Yes?
Yeah, and I also noticed another problem. That, this may be more practical. It's like when we write a paper, maybe there are 2 baselines we can choose.
Mm-hmm.
And I think and when we compare our method with the 2 baseline, maybe the slowdown is very different.
So you have baseline as baseline 1 versus baseline 2.
So like there are two options. You can choose. Either one can be our baseline.
This is a common baseline that we discussed
Yes.
for IPC alone.
Yes.
Okay.
Yeah. And then maybe it's like when we have our method, we calculate the slowdown for each kind of baseline, and the slowdown we calculate is very different.
That's right.
Yeah. So it's like, for example, if the baseline for different thread is 1, 2, 3, and our the time for each baseline. The time in baseline case for each thread is 1, 2, 3, and our method is like just 2 times of this time. So the maximum slowdown will be 2.
That's right.
But if we change if we choose another baseline, maybe it's different.
That's right. The slowdown numbers will be different.
Yeah.
But as long as you compare to the same common baseline,
Yeah.
hopefully the relative performance that you get will be not similar, I'm going to say, but you'll get a common baseline, right?
Yes, we get a common baseline, but maybe later I can do a.
Okay, sure.
example.
Think about an example.
Yeah.
Maybe you can. It's good to think deeply about this. I'm curious if you can find the perfect solution.
Yeah, just some concrete examples.
Okay.
Yeah.
Yeah, read these papers also. Actually, there are a couple of other papers, but I haven't read them, so I'm not going to recommend them yet. But if you follow the work from the same group, Andres Sesnek's group, there are a couple of other papers related to this. Okay, what else?
Yeah, the fairness.
Mhm.
The fairness, yeah. I think those two metrics are just based on how they understand the fairness.
Mhm.
But I think it should be like measured in a level variance way, like how you count variances.
That's right.
Yeah.
So you could, instead of having this max divided by min, you could actually look at the variance and slowdowns, right? Actually, that's one of the metrics in this paper. Standard deviation is one of them, for example. I think standard deviation achieves that. Standard deviation of the, I don't know what this is, but standard deviation of the slowdowns you can take, right? That's another metric that has been proposed. That's a different definition of fairness now, right? That's less strict than this, what I showed over here, maximum divided by minimum. Although it's kind of similar. Yeah, take a look at this paper. This is a good read for 4 pages. Could get you thinking. Okay. What else? We've discussed the project idea and metrics. That's good. So you can actually talk about, in your proposal, you can talk about what metrics you will use or you plan to use. Or maybe you change your proposal topic today. You'll look at performance metrics for multi-threaded processors, which is also fine. So let me actually tie the end. We were looking at these different cases, right? No. Good thing that I have 4 fingers in this hand also. Could use multiple hands. Okay, so we looked at multi-program workloads, multi-programmed single-threaded applications. But there's also, finally, multi-programmed multi-threaded applications, right? What is the metric for those, right? I think the metrics for this case and this case are actually similar, except you cannot use IPC for multi-threaded applications. You just use execution time, right? But then you'll have to execute the application in its entirety. That could take a long time. So now how do you measure the performance of a multi-threaded application and summarize it? What's usually done today is you take, because in a multi-threaded application, you really want to have an execution time. Sampling something usually doesn't work. And people have looked at how to sample parts of the program to get an accurate representation of the execution time of the entire application. But we don't know how to do that yet. But one common method today is you basically insert a marker to some location in the source code, begin marker, and an end marker to some other location in the source code, and you look at the performance between those points. So you basically execute a part of the application in its entirety of that part. And that gives you an execution time. And you can do that for all of the applications in your multi-program, multi-threaded workload. And now you can change, basically you can use the weighted speed up definition with t shared divided by t alone, right? How long it takes to execute that little chunk in your application. You can measure the performance of that and calculate the weighted speed up and harmonic speed up metrics for all of the multi-thread, for the workload, for the entire workload. That's a commonly accepted way of doing simulation. Then the key question is, how do you determine that chunk, right, in your multi-threaded application? Is that chunk representative is another question. So these are all interesting issues that you run into in simulation when you're trying to design a new system and simulate it. What else? Is there any question online? No. Okay. I guess we do have 6 participants online. Sure.
So a lot of the papers we read offers drastically different designs of computer architecture. For example, the multiscalar is one radically different design, or maybe even run-up execution is sort of different from what we're doing right now. Now, I have the question is, back in the 90s, well, back in the 80s, it was feasible to go and actually experiment with this design, not to fabricate it, so you can meet special users. But nowadays, with Intel and those big companies pushing out chips that are faster and faster steadily, is there still any point of designing really complex and deviant hardware?
Okay, let me try to break down that question. Is there any point in designing the hardware itself, or is there a point in looking at the ideas?
Well, you look at ideas because it could offer you a way to design a new system.
Mm-hmm.
However, the cost of designing hardware is very different from the cost of designing software, because you have to spend a lot of capital to actually build it. So if you're examining a really exotic idea, chances are that by the time anyone builds something using this idea, Intel and AMD are probably so far ahead that you could just buy a whole bunch of chip processors that could do the same job in the same execution time, the same performance, but a much level price point.
So that's always an argument, but so that assumes that the current state of the art is a good way to go, right? You design some particular core, and that execution model. I guess I'll take run-ahead execution, for example, so that I can give you a more precise answer, maybe. The key question is, does run-ahead execution add any value to a system that will be designed n years out, right? I think that's your question is, right? Or can you get the benefits of run-ahead execution in some other way? Is that what you're asking?
More or less.
Mm-hmm.
So what I'm really saying is, well, I think run-ahead execution could be implemented in all the current CPUs. But there are some architectures that we have been reading that really requires drastic changes to the current model. And in order to, and maybe yes, they offer good performance improvement maybe for memory intensive application or for some type of application. But that's theoretical. To bring it into practice, the cost probably doesn't offset the benefits you gain from it. So my question really is from a computer architect's perspective nowadays. Wouldn't it be better to push forward in the current model instead of exploring drastically different
I see.
models?
Okay, now I understand your question better. Should we explore drastically different execution models if their cost and cost does not outweigh their benefit? So that's something important. So first of all, when designing new execution models, it's important to be cost conscious. There's no question about that, because we're all engineers, right? It's important to design systems that are cost effective. But one of the functions of the research is actually to generate ideas that can affect future systems. And if you're extremely cost constrained, you may not be able to develop those ideas that other people are not thinking of. So one of the functions of the research is to think differently, right? And if everybody's thinking like Intel, then how would you design the system from 20 years from now, right? So I think even though, for example, I'll take multiscalar actually. Multiscalar was never cost effective, in my opinion, but it was a great idea. I think that's why I teach it in this class, because it has spurred a lot of research in directions that people didn't think about at that time. For example, memory disambiguation, as we talked in the lecture, the address resolution buffer, those were ideas that got into existing systems after the multiscalar research. So I think from a research perspective, yes, we should definitely look into different execution models, because those execution models may not be cost effective and may not be implemented ever, but they may actually lead to ideas that can change the systems. Like one concrete example of multiscalar, everybody's familiar with multiscalar, right? You've watched the lectures. Yes? Okay. I don't remember which speculation lecture this was in, but one concrete example of multiscalar is when you have these different threads that are partitioned arbitrarily or in some way, you have this communication between the threads. And you need to somehow disambiguate the loads and stores of the thread such that you can get the right data from the right thread. And they proposed something like address resolution buffer. That was one of the initial thoughts. And later they proposed dynamic speculation and synchronization and data dependence, which is basically memory dependence prediction. The idea is, can you predict the dependence of this load on a previous store? And they had some methods to do this. I don't think I've assigned the paper, but I guess I'll show you right now. Say it again?
You assigned the paper on multiscalar.
On multiscalar, yes, but not the memory dependence prediction paper. No. This was Andreas Moshov's thesis. Let's see. We go back 1997. There you go. This was ISCA 1997. And if you look at this paper, this basically, yeah, we can actually read the abstract briefly, if you want. Yeah, in this paper, we demonstrate that as dynamic instruction windows get larger, significant performance benefits can result when intelligent decisions about data-dependent speculation are made. We propose dynamic data-dependent speculation techniques to predict if the execution of an instruction is likely to result in a data-dependence misspeculation, a load. If you execute it, will you get the wrong data? Because some other store has not executed yet that writes to the same address. And to provide the synchronization needed to avoid a misspeculation. Experimental results evaluating the effectiveness of the proposed techniques are presented within the context of a multiscalar processor. So this was all evaluated within the context of multiscalar. If you read the paper, it's all about multiscalar, which didn't exist. But a lot of the ideas that were in this paper actually are in processors today. In fact, there's a story about this paper. It's kind of an unfortunate story, I think, but basically this was patented by the University of Wisconsin at the time. And I don't know if you followed any patent lawsuits recently, but Wisconsin sued Intel because of this patent. And they made quite a bit of money on this particular paper. So this is an example of looking into execution models that people are not looking into and finding problems and providing solutions within the context of that execution model, and a major company taking those ideas and actually implementing them as part of their memory dependence predictor in an existing processor. So there are unforeseen benefits of looking into different execution models. In addition to potentially you could change it also, right? More so today, actually. If you come out with an execution model that relieves the task from the programmer significantly, you could potentially have a lot of impact with that model today. And this is more so than in 1997. Because in 1997, we were at a point where single core processor performance was easy to improve, right? Single thread. So it was a lot harder to change the execution model at that time. Today, we have all multi-core. It's easy to design, yes, but it's terrible for the programmer. So if you come up with a much better execution model that can get good performance, at least at reasonable cost, I will say. Your cost may increase, but it needs to be reasonable. And what is reasonable depends on how much tolerance you have to cost, of course. But it's easier to change the execution model today. Yes?
Yeah, so I just had a question about the whole multiscalar model. Why did it never take off? I mean, I read some papers which compared it with the superscalar in terms of performance, exposed ILP, as well as complexity and scalability. And it says that it's pretty close and is workload dependent. So why?
It's pretty close in terms of performance to which one?
A superscalar.
Okay.
Out of order superscalar.
Okay.
Like factory. So, but it's a lot more scalable in some sense. So, why is this model? What's the deal breaker?
Yeah. So that's a good question, right? That's not an easy question to answer in any research proposal, right? One of the things is it does change the execution model. It does change a lot of things in the stack, right? Now the compiler and someone needs to form tasks. And those tasks, you need to have this distribution engine that distributes the tasks to different cores. And you need to have fine-grained register communication, which was something we discussed in the lecture, which is actually a downside of the model, I think. That fine-grained register communication is at a very critical path of the pipeline.
So you equate that to the register dependency checks that you would have in a really large out-of-order superscalar.
But exactly because of that reason, real large out-of-order superscalars are not there today, right?
Right. Why not multiscalar?
I think the argument is cost again, right? At that point in time, it was very difficult to change the microarchitecture. Now, this is not changing the microarchitecture, it's also changing the ISA as well, right? So that could be one of the reasons. Well, you do need some ways of communicating this information about tasks, right?
Well, the compiler does.
The compiler does it, that's right. But that means that the ISA is changed. At some level, the ISA is changed. You could certainly say you have a binary translation layer. You could play with the trade-offs as long as you have a different translation layer. Sure, but that adds additional cost. Right. So I think it required a lot of changes to a lot of things. That could be one of the reasons why it didn't take off. At a time when it was relatively easy to crank out faster superscalar engines, right? But it did have a lot of issues similar to superscalar engines also, like the register. Fine-grained register file communication is an issue. As you said, if you build a large-scale superscalar out-of-order engine, you have a similar issue, even if you cluster it. Actually, when you cluster it, you have that fine-grained register communication, right? And that's one of the reasons that we've discussed in the multi-core lectures as to the lack of scalability of these engines. So multiscalar had that lack of scalability also, I think, if you're looking for a technical reason. It's not easy to actually get the ideas into products, especially if you're changing lots of things. If you're doing more localized changes, for example, if you're designing a simpler branch predictor, it's a lot easier to get that change implemented, right? Or a better branch predictor.
Well, isn't this just in a series of evolutions? I mean, there were a lot of changes when you moved from in order to out of order, and then single issue to superscalar, and so on and so forth. So it could have just been the next.
With multiscalar? Well, again, if you look at in order, let's say single issue, multiple issue in order, that doesn't change the interface, right? The ISA stays the same. You don't need to change the compiler. Similar, again, if you move from in order to out of order, you don't change the compiler.
Well, people were open to VLIW.
So that was a totally different domain. Again, you could argue that VLIW architectures have not been as successful also, right, in the general purpose domain. Because it did change that interface significantly. Now, I'm not suggesting you should not change that interface. I think it's great to do research in all of this because it's important, because a lot of the concepts in VLIW, for example, influence the compilers today. Like superblocks, hyperblocks, trace scheduling, all of those concepts are in today's compilers, and they help superscalar compilation as well. But does that make the idea successful commercially? It may be difficult, right? Because once you change that interface, all of the software stack needs to be rewritten. The data flow was another model that we discussed in 447, and we'll get to that also. That was very promising also, right? Especially in the 70s and 80s, and as far as early 90s. But it requires the software stack to change dramatically. Yeah.
Do you think that it would have been different today if multiscalar was introduced recently, in a different context?
Could be. It's hard to tell. Could be. But I think today, my feeling is a new execution model today has much more of a chance of success than it was when multiscalar was introduced. Because at that time, people knew how to build scalable out-of-order engines for that time, for that point in time. Today, we do not know how to build more scalable engines, at least for single-thread performance. So even restrict the data flow architectures that could be more efficient, maybe at coarse-grained data flow, could be very interesting to look at today. So I think your question makes sense in that. Yes?
One problem about multiscalar is that I think the performance gain doesn't necessarily justify the cost. Because in comparison to maybe, say, superscalar, it is a lot more costly because you're really having entire cores running on each task instead of just a functional unit. However, the performance gains weren't as good as desired. For example, 8 units, the gains were like 5x for the maximum, while the average was hovering around 2x to 3x. And some of the benchmarks actually only had like 1.1x or like a minimum improvement. So I do not think, so that's sublinear, definitely. And in the current environment, a system is very likely to be running at least 4 threads or at least 10 threads. It is highly unlikely to see a system running only one application thread, that's it. So you might be better off using those extra resources to just running extra threads in parallel instead of putting them all together to run one application and only spitting out by like their number of cores divided by 2 or even less.
But you could argue that actually right now, transistors are almost free, right? You can integrate as much as you want.
Right?
You can have both. You can have a lot of cores doing single-threaded performance and also the multiple cores as well. We're right now the bottleneck for single-threaded performance, right?
That's true. What I'm trying to say is that in the current system,
so cost is not so much an issue now as it was then, would you agree?
So I'll take issue with that. Well, I'll continue. I agree with both of you at some level.
I mean, I'm looking at opportunity cost. So instead of spending those transistors in doing multiscalar, you could spend it in adding more cores that run in parallel.
Well, you need the programs to run in parallel, and that's something you can't control.
But you can have many programs, right?
Well, programs may not be parallel. At the end of the day, you still need single-thread performance.
Right.
I think that helps with that way.
So if performance is absolutely necessary, I think programmers nowadays just go and try to make the program more parallel. And for example, programs running on HPC or other type of super parallel system, they are highly parallelizable. And for everyday programs,
yeah, but if it's parallelizable, then you should definitely go that way. But I think most of them are not actually.
Yeah. So I think there are programs that are used to parallelize, right? In that case, programmer effort is not high, and they can exploit the parallelism that we have today, perhaps. But I think the difficult problem is for those not hard to parallelize programs. In that case, the programmer effort increases so much that execution models, maybe like multiscalar, could be interesting. Now, I'm not saying multiscalar has the right trade-off in terms of performance benefit versus the hardware cost. I could potentially agree with you. Actually, a lot of these thread-level speculation approaches, including thread-level speculation that we've discussed in class, they use multiple cores, but their performance benefits are very sublinear. Like if you look at the thread-level speculation paper that we discussed also, the performance benefits are on the order of 15-20% with 4 cores, right? Is that a good trade-off? If performance is really, really important for that critical piece of code, yes, perhaps, right? For some domains, that could be good. But that also means that there's a lot of potential for research in these new execution models. Maybe we get to a better performance trade-off with such models, right? So for some applications, perhaps multiscalar could be good, where you gain 4x, as long as you cannot get those gains easily with little programmer effort. I think the key argument for these execution models is minimizing programmer effort in hard-to-parallelize programs. If you can come up with a good execution model that provides good trade-offs, like good low cost and high performance in those hard-to-parallelize code sections, then you can change things significantly. And look at it another way. These models are, in a sense, orthogonal as well, right? Today, the systems that we have will be increasingly heterogeneous. So you will have that parallelism that the programmer can exploit. But we should also perhaps dedicate some of the resources to an engine that can execute single-thread programs really fast. And perhaps multiscalar, I'm not saying multiscalar is the thing, but another execution model could be employed in that core that's optimized for single-thread performance. So let me handle the cost issue also. So cost is always an issue in systems, because in the end, the system cost affects everything, right? You don't want to. So one of the arguments today that has been made is also area is free. Now, someone can think that area is less important than power, but it's not free. It's definitely not free. Why? Because if your area is larger, then you'll have fewer chips in a wafer. Basically, that's affecting the bottom line of your company significantly. So area is not free, I think. But it could be less important than energy, depending on your design point, right? So I think cost will always be an issue in designing systems. If you come up with a less costly system, then you have the competitive advantage. I think in the lecture I gave the example of the HPC systems, right? So you could argue that cost is not an issue in those systems. But even those systems, Cray, for example, used to build specialized vector processors, very specialized, in the early 70s. And actually, I showed a picture of that, right, in the heterogeneity lecture. Remember that Cray 1 computer system, Richard Russell, CACM 1978? Yes, that paper. Actually, it's an example of a heterogeneous system, right? You have a vector processor and a scalar processor, and it was the fastest scalar processor of its time. So that was very specialized. But cost became a significant issue for them also. So what did they do? They started using microprocessors in designing their supercomputers, right? That's called the attack of the killer micros in the 70s. Basically, everything became microprocessor-based instead of specialized supercomputer-based. And the reason was cost, essentially. Not only cost, but they also realized that you could get similar performance in their HPC workloads with these microprocessors and tying many of them together.
That's actually a good question. So nowadays, if someone gives you a budget of say 1 million to build a huge HPC, is it still more cost efficient to just spend those 1 million buy a lot of CPUs and GPUs instead of using it to actually design and fabricate one highly specialized hardware?
Today, you're asking. Well, I don't know the answer. Depending on your processor, depending on the processor you're designing, you might want to do specialized hardware. But I think what you're getting at is another trade-off, which is, do you design specialized hardware for your problem, or do you use more general purpose hardware? Again, you'll need to make the trade-off, right? Depends on how much you value performance with the specialized hardware, how much actually you can get with that specialized hardware, and how much the additional cost is. I'll recommend one paper. I think I don't think I can give you a precise answer because that's a very tough answer. But people have tried to design specialized hardware for many, many reasons over time, and sometimes they've been successful. A lot of the time, the difficulty is you design your specialized hardware at this time, and the regular hardware improves its performance. So at the future, when you're actually using your specialized hardware, where will your regular hardware be, right? And usually that regular hardware is so fast improving in performance that by the time you design your specialized hardware, it's just too late. Right? But there are some problems that are critically important where specialized hardware can potentially help. One of them is, I'll recommend another paper to you. It's not clear. I think the jury is still out whether this will be a good idea or not. Yes, he does have papers. That's good. Yeah, this paper. This is one of the more recent, one of those specialized machines, Anton. I don't know where we're downloading this from. Chile. That's why it's slow. Let's try somewhere else. CSCMU. That sounds faster, right? Yeah. This was a machine that was designed for basically molecular dynamic simulations to speed up drug discovery. And they've actually built this machine. And I bet there are some performance studies recently. I haven't followed up on all of the literature. But I'd encourage you to look at this paper. And this was a concern for them also. Do we design the specialized hardware for molecular dynamic simulation? Or do we actually use the hardware as it grows faster? And there are some, this is the initial paper. This is in ISCA 2007. But it talks about different things, for example. I guess this is the processor, I don't remember what they called it. Pairwise point interaction modules, for example. That's the specialized. This is to compute the forces that happen in molecular dynamics. You can read the paper for more detail, but you can see specialized hardware here, right? Electrostatic function evaluator, van der Waals function evaluator. I think all of your chemistry should come to your mind now. But this is the specialized functional unit they have in their hardware. And they've shown, I think, performance benefits of like 1000x or so. I don't know if it was here. Yeah, there you go. And this is in simulation, I believe. But they have a prototype system. And I'll need to remember what it was. Yeah, there you go. Anton benchmark. And I don't know what that production is. But you can see performance benefits of up to 10,000x compared to some comparison points. I guess Blue Gene L, maybe. That's a less specialized supercomputer, right? IBM's Blue Gene. Although it has some specialized functions, but the processor itself was not specialized. So you can take a look at this paper. But whenever you're designing specialized hardware, you're taking a risk because of this, because your costs are higher, and you're competing against something that's improving continuously. You have a moving target. So you'd better have a really good application that moving target cannot reach. Right? This could be one, molecular dynamics, but it may not be also. But at least now you have a very good paper to read. Yeah, it's from D.E. Shaw Research. I don't know if you know the story of D.E. Shaw Research. Anybody familiar with that? So D. Shaw was a professor at Columbia, and then he formed this company that basically accelerated stockbroking, brokerage transactions. Not only accelerated, but also did a lot more data analysis. And he made a lot of money out of that company. And then using this money, he's building the specialized hardware now. That's a very short description of it. You can read more about it, certainly. But it's a very successful company that does other things, but it's not clear if this one will be successful. What else? Any other questions on anything? Yeah.
Like in our simulation, we need to like feed in multiple apps, applications, and I want to know how to choose those apps. Like it could be tricky. Like if you choose two of them run simultaneously, like each app has its own feature, whether it is memory intensive or something else. But there's another comparison, like if you choose 2, 3, or 4, like the number of apps, it could be another comparison. So I want to like hear your opinion.
Yeah. So that's another tough problem. Whenever you do evaluation of a multi-core system, how do you choose the different workloads? Let's assume that they're single-threaded applications. How do you choose the different single-threaded applications that are running on the system? Because the combination explodes, right? There are many combinations you can have. And you cannot possibly simulate all possible combinations, right? If you have 24 cores and maybe 50 applications to choose from, I don't know, you can calculate how many combinations you need. That could be a good exam question, maybe. But again, there's no easy answer to that. There are several ways people take. One is you can randomly select a large set of applications. And that large is, again, wishy-washy, right? What is large? You could take, the larger the better, I will say. But you can take 500 different combinations, and you could simulate that. That's better than what would be commonly seen today. Now, on top of that, what can you do? I think a good idea is to actually categorize the applications and try to form different categories. And this depends on what you're examining, right? For example, if you're examining memory scheduling, memory intensity could be one metric to evaluate different combinations. You can have different combinations at different memory intensities. Memory intensity means how much time, how many misses is the memory controller seeing from the entire workload, and categorize your performance based on that. Right? Now you could go even finer grain, right? You could categorize the applications based on the robot for locality and bank level parallelism and other potential metrics. But that makes your life harder and also the analysis harder if you would like to combine these different applications. Especially with with more than 4 cores, it becomes really tough to categorize applications and make sense out of the results. But I encourage you to do that still. So I don't know if that answered your question, but the more applications, the more workload scenarios you simulate, the better. And the more categorization you make and look at the performance differences or benefits of your mechanism across different categories of workload, the better. Because that gives insight. Also, in the end, when you're doing research or when you're doing your project, the goal is to reach some insight. Right? And if you can say, this kind of applications, memory-intensive applications, benefit from this optimization better than other applications, that would be useful. But this is really dependent on your specific problem.
Yes, but it could be like you have different combinations of apps, and it could benefit some of them alongside with running another kind of app.
That's right.
So if you have like a lot of memory-intensive apps running at the same time, it could be not that beneficial.
That's right. That's right. Yeah. So your performance benefits can depend on the mix of applications, and that's a tougher one to evaluate, right? But you could, what we've done, for example, if you look at the atlas, so this is another paper that I would recommend you to read. Actually, I'll show you a particular categorization here, if I can find it. Yeah, I guess I'll be able to find it over here. Maybe. There you go. Yeah. So this is one categorization that we did. This is a coarse categorization. But basically, you have 24 core system, 4 memory controllers. And we'd like to look at the benefits that we get in different application categories. One way of categorizing the application is the number of memory-intensive benchmarks in the workloads. And you define memory intensity in some way, basically. A workload is memory-intensive. An application is memory-intensive if you have more than n misses per kilo instruction going into memory. 0 means you don't have any memory-intensive applications with that definition in the 24 application workload. And as this increases as you go. 24 means all applications are memory intensive in the 24 core workload. And this data is averaged across, I don't know, how many respective benchmarks we run in each category, maybe 32. So what this shows is basically the benefits of Atlas memory scheduling algorithm, which you haven't listened to, but we briefly talked about in one of the recitations, is highest when you have a balance between memory intensive and non-memory intensive workloads, right? This is the percentage performance improvement of Atlas compared to the best previous mechanism. And it's 8.4 here. It's maximized here. It's minimal here, 3.0%, because you don't have that much memory intensity in the workload. It's minimal here because all of the workloads are memory intensive and scheduling may not help that much. Memory scheduling may not help that much. It's maximized here because now we have different kind of applications in the system. And scheduling helps because you have a wiggle room, if you will, in the scheduling. So this is one way of. So this graph actually gives a lot of insights. If you have this kind of graph, I'd be happy with your report, for example. So this shows several things. This is kind of beautiful, in my opinion. This basically shows the system throughput in terms of weighted speed up, and this shows that weighted speed up is high if you have less memory intensive workloads. And this makes sense, right? Because weighted speed up is the sum of speed ups, IPC shared divided by IPC alone. And that's closer to, so what is the ideal weighted speed up you would get? It's 24, right? Compared to the same baseline, let's assume. Because we're not changing the baseline here. The baseline is some scheduling policy on the same system. We're just evaluating the performance of Atlas. It's really 24 because ideally your speed ups are all 1 when you're running shared compared to when you're running alone in a multi-programmed workload. This shows that you're getting closer to 24 with 0 memory intensive benchmarks in the workload, which means that threads are not slowing down that much. And that makes sense because if you're not memory intensive, you're not interfering in memory. Whereas if you look here, this weighted speed up is, I don't know, 4. Much farther from the ideal of 24. That makes sense because all of these threads are memory intensive, which means that they're interfering in memory and they're slowing down each other. So this graph nicely shows that. As you increase the number of memory intensive benchmarks in a workload, the absolute value of the weighted speed up keeps decreasing. That's beautiful. And also it shows this other phenomenon that I described over here. The percentage performance improvement is dependent on, actually if you plot that, it's lowest here and it increases and peaks here and then it goes down. Yes?
The first 3% makes sense because if it's not memory intensive, Atlas isn't really doing anything.
That's right.
But
Exactly.
why does it fall off at the end?
Over here? Because memory is oversaturated in this case, saturated a lot.
But should Atlas provide a better utilization? So it should still improve compared to the other ones.
It does, 4.4%. But it's less than here.
Yes.
Why? Because here, all of the benchmarks are similarly in terms of intensity, right? They're probably highly memory intensive. So Atlas, there are two reasons, I think. One is all of the benchmarks are similar in terms of intensity, and which means that prioritizing one over the other doesn't help performance that much. Whereas if you have some compute-intensive workloads, prioritizing that over the memory-intensive ones would help performance a lot. That's why this gains better. And the second reason is scheduling helps you in cases where you have some extra bandwidth, right? Here, if you're oversaturating your memory bandwidth, and if your applications are actually similar, then you shouldn't gain that much benefit from scheduling. Here, you shouldn't gain that much benefit from scheduling because scheduling may not be a problem. Although in this case, it is a problem because of the definition of memory-intensive workload, right? So it's good to have graphs like this. So I'd recommend this paper as a potential project report. There are other graphs over here too, basically performance with varying number of cores and memory controllers, and this shows similar trends over here. Now, does that answer your question? So that's one way of actually categorizing the workloads. Another way of categorizing the workloads would have been also looking at the similarity of the threads, right? This is a harder way of categorizing the workloads. Like, how similar are all of the 24 threads in terms of MPKI, misses per 1,000 instruction? And you could have a category that's threads are very similar, threads are very different, and some metric to decide that. And I believe that would show a trend also in this case. If the threads are very similar, Atlas likely doesn't help. If the threads are very different, then Atlas probably helps. More questions?
I have questions on the lecture.
Sure.
So in multiscalar, you mentioned that all the later tasks, if you will, get squashed, have to be squashed if you misspeculate. So why is that necessary here?
If you misspeculate in terms of data dependence, right?
Or a branch?
Or a branch. If the branch misprediction is internal, then you don't, right? And if it doesn't affect data.
Even if it's external?
If it's external, yes. Yeah.
Why?
Why do you squash? Well, it's simple. That's the first step. It's actually simple. And I'll say that it's simple. You don't have to, right? As long as you track the data dependencies.
Which you're doing anyway.
Which you're not doing because you've executed all those instructions, right? You're doing it while the data gets propagated. But once you've executed those instructions, you've forgotten. Unless you record it somewhere, which makes it more complex. Right? So it's really the data dependency propagation that you need to record somewhere. So based on this potential speculative value, which instructions have I executed? So you'll need to re-execute only those instructions.
No, I mean, if there's a data dependence, then obviously you need to re-execute.
Sure.
But if you can track data dependencies which you're doing, and you determine that there in fact are no data dependencies.
They're in fact what?
No data dependencies.
Okay. So, but you need to record that somewhere, right? To be able to do that efficiently.
You know it already. You have the mask, right, to tell you which registers are like. And if you know that there aren't any, then why would you squash?
Simplicity.
Okay.
So it's a lot simpler to blow up everything, like blow up the entire pipeline, and start re-executing, right? Because you could say the same thing about run ahead also, like you've executed all these instructions, and why do you go back and re-execute? Again, simplicity.
What do you mean?
Because tracking all of those data dependencies is expensive,
Oh, okay.
right? To re-execute, yeah. Yes, you discover those data dependencies when you actually execute the instructions the first time. But re-executing requires rediscovery again, or keeping it somewhere and re-executing only those instructions. Yes?
I think it's about like how detailed the memory of the system is. Mask is not very precise. It it can tell you what happened, like it can tell you exactly at which point what happened. And if you want to keep track of exactly the execution order and every instruction, and they could be interleaved, right? Some instructions could be correct, some others are not correct. You need to find the correct interleaving of them, and then individually pick those instructions out and re-execute them. And then you put in a really huge stack, that random accessible stack or something like that, that allows you to.
Well, that would be true in run ahead, but I thought that multiscaler actually enables easier selective execution.
But not within a task, right?
Yeah, no, not within a task, right? Within a task, you still need to figure out the data dependence.
Not within a task, and
Yeah.
between tasks.
Yes, between tasks you know potentially, but again, you don't know perfectly, right? You have a superset because there could be memory dependencies again. But within if you want to do selective re-execution, you need to selectively re-execute within each task.
Well, it's just a question of not squashing and squashing. That's just what I meant by re-execution.
Say it again.
So I just meant instead of squashing it, you just selectively squash and re-execute those.
That's right, but that's the same problem, right?
Yeah.
You need to figure out what to re-execute and what not to re-execute.
Don't you think it would be slightly simplified with this model?
I think it's similar.
Similar?
Yeah, I don't think multiscalar helps that much in selective re-execution. It's similar. So selective re-execution has been implemented actually, and Pentium 4, Intel Pentium 4, for example, what it does is you get a load cache miss, and what it does is you determine the cache miss late. Once you figure out that it's a cache miss, you already speculatively scheduled dependent instructions because it's the deep pipeline. So what it does is it takes all of those instructions out of the scheduler and puts it into a pipeline, FIFO queue in data flow order. So you have the load, dependent add, dependent add, dependent add. All those instructions get drained out of the scheduler. And it's placed into this FIFO queue. And later, when the load miss comes back from memory, you start re-execution out of that FIFO queue. So you need that additional FIFO queue. And this actually caused them a lot of problems at Intel. This is called the replay loop. I don't know if you're familiar with that. But it's called instruction replay. Basically, you're replaying this load instruction that missed in the cache and all of its dependents. Now you need to, it complicates the pipeline. What you need to do is, because you're also scheduling other instructions here, and now you need to actually put instructions from the replay loop into the pipeline. Where do you put them? That was one of the issues they had. And which instruction do you prioritize? An instruction from the replay loop or an instruction from here? I can recommend you some papers, but it does add complexity. Eventually, the argument is complexity. Do you keep those instructions nicely in the scheduling loop? And so in this case, it was a load hit miss issue. But you could imagine a memory dependence prediction, right, in an out-of-order engine. When you predict the dependence of a load, you could do the same thing. You could selectively put it into a FIFO queue. And if you're doing it for many different dependencies, now you need many FIFO queues, potentially. Or maybe a single FIFO queue, but then you need to figure out which instructions to execute for these different dependencies. So complexity becomes easy. Complexity becomes easily less tolerable. Right. There's no fundamental reason why you cannot do it, but you need to design the hardware to operate correctly. Okay. More questions? We've gone the entire 2 hours. Yes?
I was just wondering if you could talk a little bit about the paper that we had to read yesterday, the dual core execution. I was just kind of wondering, like, since that was published, I think, in like the last 10 years, like, what the importance of that was, and I guess like how it shaped what's been going on the last 10 years. Because I was just reading and I was like having a hard time like visualizing, I guess, like the importance of it, I guess, or of it being like unique, I guess. I don't know, because when I was reading it, it kind of just came across as like another way of like doing some sort of pre-execution or something.
That's
like, well, how is this like so much different?
So it's definitely another way of doing pre-execution. It's similar to a lot of those ideas on slipstream processing, right? You have one core going ahead and doing things for the other core. That's the idea in dual core execution. You have a front core. When it gets to a long latency cache miss, it does run ahead execution and feeds those instructions that are executed to the back core using a FIFO queue. And now back core can execute faster because it has a nicely predicted instruction stream. And hopefully the front core is not stalling and prefetching data into the caches. Now what you can do is you can extend the length of that FIFO queue and make it really large, and you have a very large instruction window. That's useful when you have a long latency cache miss. Right? So in this sense, it's similar to a lot of ideas, like slipstream processing. You've watched the lectures, right? You remember the idea. Is similar. It tries to do the same thing. Except this is a practical way of doing slipstream processing, in my opinion, because it's really easy to run ahead in the first core, in the front core. Whereas if you look at the slipstream paper, you need to get rid of some of the instructions somehow. And how do you do that? Basically, you need to detect dynamically dead instructions. So there's a lot of complex logic involved in the slipstream processor that we've discussed in lecture. So it has a different take on how to design a slipstream processor. It has a different take on pre-execution also, because it's really not doing run ahead in a single core, but doing run ahead in a multiple core context. If you have two cores, then you can do run ahead on one core, and you could do redundant execution in the other core, and have a very large instruction window. Like one of the difficulties in scaling run ahead is you're doing run ahead in a single instruction window, so your run ahead needs to end at some point, right? Because the speculation that you're doing is preventing regular execution once your load miss comes back. Whereas in dual core execution, the speculation that you're doing can continue on while you're actually doing useful work in this core. So I assigned this because it ties together a lot of these different concepts in a nice way, I think. So what kind of impact has it had? I'm not sure. That one's a tougher one. Sometimes you don't have impact at all. Sometimes it's just a cool idea. I think in this case, I don't know if it's impact, but I think it's a good, more realistic and more implementable take on this slipstream-like architectures. And in a way that overcomes some of the disadvantages of run-ahead execution. The downside is, of course, cost, right? You have these two cores doing, trying to improve performance.
Well, in this case, the other core can actually execute another thread if required.
If required, yes. But then you're not getting the benefits for a single thread.
I mean, if it's idle, then you could use it.
That's right. Yes. So it's more practical,
Yeah.
right? That's right. But that's true for a lot of the slipstream-like approaches also. If you don't have to do slipstream if you have another thread. Okay, shall we call it a day, or?
We have a question from online.
Okay.
Regarding the dual core execution and why it doesn't make sense to reuse the instructions that were executed correctly.
Let's see, where's this online thing that I have? Okay, so the question is, go up. Can I go up? Yeah, right there. Yeah, I guess it's a similar question that you had, huh? Yeah, commercial success. Yeah, I don't believe this is implemented in any processor yet. Further reading on optimizations over DCE, power consumption and repetitive instructions, I was thinking. Since we have an invalid bit propagated all along, can we go one step further and classify instructions in the result queue as valid or invalid? And based on that, we could prevent re-execution, basically add some level of correctness even to the results from the front processor. Well, actually the paper, the dual core execution paper evaluates this, and they don't see much benefit. I'd encourage you to read the paper.
Yeah, I told them that any further asks.
Okay.
Could you scroll down to the very last question?
Okay, sure. This one?
Yeah.
Since have an invalid. That's true, yes. But if it doesn't provide any benefit, then re-executing is simple, right? So I'd encourage you to read a couple of papers related to this. Let me find out. I think you provide the reference. What is 24?
24 is on re-executing instructions.
Oh yeah, that's what I was going to recommend also. So let me recommend first one of Hu Yang's papers. Where is that? Oh, this is going to be tough to find. No, it should be. Do you see it? Or yeah, there you go. This one. Oh. Yeah, I would recommend this one, optimizing dual core execution for power efficiency and transient fault recovery. So this does evaluate some of the ways of eliminating the additional instructions. And you can take a look at that. It's good analysis if you're interested in that. Yeah. Actually, I'm not going to cover this in detail since we're out of time also. But you can see different enhancements to dual core execution. Yes, like selective invalidation, things like that. Yeah, reducing redundant execution in DCE, for example. So this paper discusses a lot of the ideas that I think Shiva was suggesting. This is one paper. The other is what we've done in the context of run-ahead. And I'll show one thing and then we'll end after that. This is the paper. This is again a short paper, so and I'd encourage you to read it. So this paper basically discusses, like you can read the abstract. It's always good to read the abstract of another paper, right? Like this paper evaluates the effect of reusing the results of pre-executed instructions on performance in run-ahead execution engines. We find that even with an ideal scheme, it's not worthwhile to reuse the results of pre-executed instructions, at least in terms of performance in this case. And this paper provides analysis that it provides insights into why result reuse does not provide significant performance improvement. So if you look at that, there are several reasons, but I'll give you one reason that I think I find interesting, at least within the context of run-ahead, which is basically this. So this is one data flow graph, but there are lots of data flow graphs like this. Let's say this is the load instruction that caused run-ahead, and these are the invalid instructions, right? You cannot execute them because the data value is not available. You'll have to re-execute only these. And this is the valid instructions that come after this load instruction that you can execute in run-ahead mode. And you have executed them. Now when you go back, what happens is you'll need to only re-execute this one in an ideal world, right? And you don't have to execute these, assuming you built that ideal world. But it turns out, in many cases, this becomes your critical path. And this becomes not so critical, because what you've done by executing these is, these loads, you've fetched them into the caches, and you've ensured that they're in your L1 cache. I mean, you don't guarantee that, but valid instructions, it's likely that you've warmed up your caches for both instructions and data. Well, data is more important in this case. So when you re-execute them, you won't get cache misses, so you can execute through them relatively fast. But when you re-execute, well, when you have to execute this one, you get these L1 misses and L2 hits in these loads that you didn't execute before. And this becomes your critical path. So not re-executing this part doesn't help your performance that much. I think that's one of the reasons that we found why it doesn't improve performance. Now, power efficiency, yes, not re-executing can improve your power efficiency, but remember that you need some additional hardware to actually ensure that these are not re-executed, right? And I'll encourage you to think about how you can design an out-of-order engine that doesn't re-execute some instructions. Because this is fine-grained result merging that you need to do. You need to somehow keep track of the results that you've generated in this. With run-ahead, it's harder, I think. With a single core, it's harder. With dual core execution, it's easier. Because you have this FIFO queue, you just append the results into each entry in the FIFO queue. So you may not get performance, but you may potentially get power efficiency by not re-executing. And it's easier to do in a dual core execution context. Okay? I'm happy to go further, but we're out of time. It's already 12:30. So if you have burning questions, you can ask. But I think one thing I will point out is we have, where is our, I guess I can point out when I have 5% battery left. Where is the course website? Oh, it should be here. Yeah, there you go. So we have added a project description document, project guidelines document, that will hopefully give you some guidelines on the proposal. So I'd encourage you to take a look at it. People have asked how long should the proposal be? It should be long enough, but it shouldn't be too long. So my suggestion is that 2 to 3 page document will provide a LaTeX template to do this, and I'll ask you to use that template. It's a good tool to learn. If you do not know LaTeX, you'll learn it, and it's fun to use. It leads to much more professional looking documents than this one, which was prepared in Word. You can tell, right? This is Word. Whereas with LaTeX, you have a more professional document. Hopefully the content will be professional too. But basically, we're looking for something 2 to 3 pages. Now, if you want to write 4 pages, that's good if you have good things to say. But just don't write for the sake of writing. And what are we looking for? The problem, novelty, the idea. What is your hypothesis? What are you going to test? What are the initial experiments that you're going to do? What methodology you will follow? So this is very important. And some of the references, like how do you build on previous work? How does it compare to what others have done? That's important too. So take a look at this document. And I expect all research projects can be described in this fashion, just like you're doing your reviews, right? Your reviews are very similar. Right? I guess in this case, you don't have strengths and weaknesses, but you can certainly add those too. What are the anticipated issues? Okay? Okay, and this is due next Monday. And you can certainly send email to me and the TAs if you need any feedback. Okay, let's call it a day then. I guess see you next Wednesday.